here we are. Let me close us up here because that's right in the middle of the white space again. And where we are in chapter 3, determinants, okay, 3.1, the determinant of a matrix, and we're on page 113, top of the page, and it's theorem 3.1, expansion by cofactors. Okay, now this is going to look, in a sense, in my mind, kind of hairy. Okay, there's an easier way to do it than the way they described. It's doing the same thing, but if you do it the way that I think I'll describe to you, it just cuts out a lot of busy work, it seems like. Okay, but here's the theorem, and because this is has so many subscripts and everything, I'm just going to write it down. I can't remember. I know you have a book, don't you, Kira? Okay. I can't remember. Did the other two both have books, or can they not see them when we're doing the class? I don't remember either. So let me write it down just for everybody. Okay. So here's what we got. Let A, my pen is not with it, be a square matrix. The pen is really jerky today. I don't know why. Of order n. Okay, now the only matrices that have determinants are square matrices. So this is an n by n matrix, square matrix, so we can talk about it. Now, not all square matrices have determinants, okay? But, well, actually they do. Sometimes the determinant is 0. So the determinant of A, that's represented by the determinant of A, is, okay, now this is hairy looking. Don't let it frighten you or disturb you or anything. It's the summation of J equal 1 to n. That's the size of the matrix. This thing is so aggravating. Okay, J equal 1 to n of Aij times Cij. I don't know if you remember what that was. It's been a week since we met. Okay, and here's what that is. That's the AI1, because you're counting up the J's, AI1 times CI1 plus AI2 times CI2 plus AI3. I can't get my pen to write. I3 times CI3. Okay, plus dot dot dot. The pen is really jerky. All the way up to IN okay, times CIN. Okay. Now, in case you've forgotten or fled the coop for a little while, or it's been a while, the A's are elements. Okay, and what you've done, you've chosen the ith row. Oh, here comes Jesus. Okay, we got 2/3 of the class here now. Got the bookends, the top and the bottom, waiting for James to fill in the middle. Okay, and there's Jesus is here. Jesus, we're on in chapter 3, determinants, 3.1, the determinant of a matrix, on page 113, top of the page, excuse me, theorem 3.1. Okay, now the pen is really jerky, so it's not all that easy to read, but if you got the book, you can see where it is there, top of page 113. And here's what they're showing you. To get the determinant of a square matrix, n by m matrix, okay, pick, they're doing a row. It doesn't have to be a row, but we'll get to that later. Pick a row. They chose the ith row, whichever one that is, the ith row, okay? Now, let's take the elements in the ith row. AI1, AI2, AI3, AI4, AI5, AI6, all the way up to AIN, okay? Now, you take those entries and multiply them by the cofactor of that entry. Now, if you remember what the cofactor is, if this is the AI1, say, okay, right here, wipe out the ith row and the first column, because AI1, okay, and then the matrix you have left, when you wipe those out, that's what they call the minor, okay? And then if you assign a plus or a minus sign to it, depending on the sum of the i's and the j's, that gives you, if that sum is even, then it's a positive, it's odd, it's a negative, okay? So that's what the cofactors are. And that's certainly correct, absolutely correct, okay? Now, another way you could express this, same A, same everything else, but this other way to express it is A, the determinant of A would be equal to the summation of I equal 1 to n. The other was counting the I equal 1 to n, okay, of A I j times C I j. Now that looks just like that. The only difference is this is counting your i's, this is counting your j's. So this would be A 1j C 1j plus A 2j C 2j plus A 3j C 3j plus dot 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 all the way up to and including C N J, I'm sorry, A N J C N J. Okay, that would be the last one. What's the difference here? You started with the ith row here, went all the way across it, multiplying the element by its cofactor. Down here you started in the jth column and went down the jth column, multiplying the element by its cofactor. Either one of them works. Okay? Now, it says here, when expanding by cofactors, you do not need to find cofactors of 0 entries, because then it's just going to be 0. If that Aij, whichever one you're doing, that Aij happens to be a 0, forget it, because it's 0 times that cofactor is still going to be 0. All right, so let's actually do this. Any questions before I delete this slide? Any? Okay. So here is a matrix. Okay, it's got to be square, and this one it's a 4 by 4. Now I'm going to show you, to me, what's a little bit easier. Okay, this matrix is 1, -2, 3, 0. Okay, -1, 1, 0, 2. 0, 2, 0, 3, and 3, 4, 0, -2. Now, I want to remind you of one little statement they just made. It says, oh, I'm sorry, I forgot to say it. Okay, the row or the column with the most zeros in it is usually the best choice for your expansion by cofactors. Okay, and that's exactly what we're going to do here. I hope I copied it right, otherwise I'll be in deep trouble, but here's what it is. So let's take a look at this. The first row has 1 0, that's not too bad. Second row has 1 0, not too bad. Third row has 2 zeros, that's even better. Fourth row has 1 0. Well, third row is winning so far. But remember, we could also do columns. First column, 1 0, not bad. Second column, no zeros, don't go for that one. Third column, look at that, 3 zeros. That's the one so far. Fourth column, only 1 0. Let's use this one right here. Okay? So here's what we're going to do. We're going to expand by cofactors of this. Now, we're going to use this one, the third column, first row, because that's the only non-zero entry there. Okay. Now, we're going to take that value, 3. The first thing we're going to do, this is where I find it far easier than dealing with cofactors. Okay, let's first determine the sign of that position. Okay, well, here's how you do that. Start in the upper left where we usually do and just start counting. Plus, minus, plus. So that's a plus. So that's going to be 3 times the determinant of this minor that's left. And that's going to be a minus 1, 1, 2, 0, 2, 3, 3, 4, negative 2. Okay. Now, I would have closed that out. They want us to do a full dealing with cofactors. But look, when you get down to a 3 by 3, do the easy step. You don't have to do cofactors anymore. If you did cofactors, you would choose either the first column or the second row because that has the most zeros in it. But guess what? Just do with what you got. Repeat the first two columns. Minus 1, 1, 0, 2, 3, 4. Now let's do, now I'm going to put the bar there as if we're doing a determinant. Obviously that's a rectangular matrix, not a square matrix, but you know what we're doing here. So this will be 3, don't forget the 3, times, and let's do the first diagonal here, down diagonal, multiply those together, that's 4, positive 4. Okay, do the second down diagonal, and that's a plus 9. Do the third down diagonal. That's a 0 because there's a 0 there. So now what I'm going to do, just because it's messy, I'm going to take off these construction lines so I'll be able to see a little better. Okay. Now do your up diagonals. Okay. Well, the up diagonals, remember, are always the negative of that. Well, this is 4 times 3. That's a minus 12 because it's the up diagonal. Here we have a 4 times 3 is a 12, but with a minus sign. But because it's the up diagonal, it's in the opposite of that. So that's going to be a plus 12. Hey, those add to 0. Not bad. And what happens here? Next up diagonal is going to be a 0. So what do we have? We have 3 times 13, which is 39. There's the determinant of that big old matrix you had to begin with. When you get it down to a 3 by 3, go on and expand your 3 by 3. You don't have to continue doing expansion by cofactors. However, you've got to use cofactors to get down there. But remember, the easy thing is, rather than having to keep up with the I plus j and doing that mess, all you have to do is remember the sign of the position. And since we're using this 3 here, that's a plus minus plus. Okay, so that's a plus 3 times times the determinant of what's left over. That was a 3 by 3, expanded out, you got it not. Let's make sure they did it right in the book. can't see where they've done it. Oh, there it is. Okay, got it. Yes, they got 39. They took a lot more effort to doing a full-fledged expansion by cofactors. It works. It definitely works. It's so much easier doing it this way, though. Any questions? Example 4. Okay. Let's move to, then they give the alternate method, which is exactly what I just did. I thought we had already done that. Sorry about that. I jumped the gun on you, didn't I? I thought we had already done that. But I think I showed you before anyway, didn't I? Okay. So when you do get to the 3 by 3, which is exactly what we did, we just expanded the 3 by 3. So let's move on, unless there's questions, to example 5. Now, example 5, you can also go to larsonlinearalgebra.com to see an interactive version of this type of an example. So here it says find the determinant of this matrix. So I think I'm going to clear what we got. Does anyone need this any longer? Okay, so I'm going to clear the drawings. I want to check and make sure James isn't here yet. Nope, don't see him yet. So hopefully he'll be coming in. Okay, so here's example 5. Here's your matrix A, and it is 0, 2, 1, 3, negative 1, 2, 4, negative 4, 1. Okay, it says find the determinant. Okay, now rather than, this is a 3 by 3, rather than doing expansion by cofactors, which you could do, I would either use the first, if we were going to do that, either use the first row or the first column because that has the most zeros. But guess what? Not necessarily. Just expand those first 2 columns again. 0, 2, 3, minus 1, 4, negative 4. Okay, and we'll pretend we're doing a determinant of that. Okay, now all you do is do your down diagonals. Okay, well that's going to be a 0 because if any factor in there is a 0, the whole thing's a 0. So that's a 0. Okay, the second one is 4 times 4 is 16. And the third one is 3 times negative 4 is a negative, yuck, so aggravating, negative 12. Okay, those are your down diagonals. Okay, I had it drawn in there, but it erased it, so I was going to erase it anyway, so that's okay. I can't get it to erase. Now, there we go. So let's erase those construction lines, and it wiped out. Goodness, now it's erasing everything. Okay, let me fill those numbers back in. It was a 2 and a 1. A 2 and a 1, and that's a 0. Okay. Now, let's do our up diagonals. That's 4 times a minus 1 is a minus 4, but it's up diagonal, so that's going to be a plus 4. The next one has a 0 in it, so that's nothing. And the next one is a 6, but since it's up diagonal, that'll be a minus 6. Okay, let's combine what we've got. 16 minus 12 is 4. 4 plus 4 is 8. Minus 6 is 2. So that should be our determinant. And sure enough, it is. Now, there is a little, any questions on that one? Examples 5. 3 by 3's so much easier rather than doing expansion by cofactors. Just go on and expand the first 2 columns and let that do your down diagonals, positive, up diagonals, negative, add them together. You got it done. Okay. That only works for 3x3s. Don't try it with a 4x4. Don't try it with a 2x2. Okay. Now, there is a linear algebra applied at the bottom of page 114. And it's talking about a tetrahedron, which is a four-sided geometric shape. Okay, three-dimensional geometric shape. Every side is a triangle. Okay, four triangular sides that form a geometric shape. It's a polyhedron, which means multiple sides, more than one side, consisting of four triangular faces. One practical application of the determinants is finding the volume of a tetrahedron in a coordinate plane. Okay, we're going to be doing this in section 3.4. Why they're bringing it up now, I don't know, but this is what it is. And I'll write it out for you, but we're not going to do anything with it until we get to 3.4. So let me just show you what these are, and it's rather bizarre but true. Okay, so if you have a tetrahedron, okay, so you have a triangular base here. Okay, there's a triangular base, and you have a triangle that goes like this, a triangle that goes like this, a triangle that goes like this, a triangle that goes like that, and a triangle that goes like this. Four-sided figure. Here's a side, there's a side, back there's a side, and there's a side. Okay, these are 4 points. Okay, x sub 1, x sub 2, x sub 3. Okay, this one would be, let's see, maybe I should call it that way. No, let's call it x1. Let me change that. Okay, x1, y1, z1. We'll call them that. Okay, x1, y1, z1. This one will be x2, y2, z2. This one would be, it doesn't matter which one, but x3, y3, z3. And this one over here would be x sub 4, y sub 4, z sub 4. Those are just points in space. Okay, now to get the volume of that tetrahedron, it doesn't have to be regular, it doesn't have to be anything, it just has to be a tetrahedron, four-sided polyhedron. Okay, the volume of that is surprisingly, now they have to put the plus or minus here, because depending on which order you chose these things to be, you may have a positive determinant or a negative determinant. We always want a positive determinant because volumes are always positive. So therefore, if the determinant turns out negative, negate it. Okay, now you also have a 1/6 here. I can't really describe to you exactly why it's a 1/6, but it has to be there. Okay, now then you do the determinant of these points. Okay, almost. The first row would be x sub 1, y sub 1, z sub 1, but we need a 4x4. So the fourth entry is just 1. The next row would be x sub 2, y sub 2, z sub 2, 1. The next one would be x sub 3, y sub 3, z sub 3, 1. X sub 4, y sub 4, z sub 4, 1. Find that determinant, you've got it knocked. Okay, that's the volume of a tetrahedron. Okay, and like they said, you're going to do that in section 3.4. Why did they bring it up now? I don't know. Okay, so anyway, you've seen it, we'll use it later. So let's clear that drawing from the slide and proceed with triangular matrices. Okay, now we've hit this before, under a sort of different context, but we've hit it. We talked about triangular matrices, okay? In section 2.4, a square matrix has to be square, is upper triangular when it has all zeros entries below the main diagonal. Lower triangular when it has all zero entries above the main diagonal. So here are a couple of triangular matrices. Upper triangular, A sub 1, 1, A sub 1, 2, A sub 1, 3, dot, 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 up to A sub 1. Do they use N here? Yeah, N. They could use any counter, okay? Second row would be 0. A sub 2, 2, A sub 2, 3, dot, 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 up to A sub 2, N. Third row, 0, 0. A sub 3, 3, dot, 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 up to A sub 3, N. Fourth row, actually I think I'll just dot, dot, dot down here and go to the nth row because it has to be a square matrix. This will be a 0. Okay, I don't know what the noise is about. If you need to talk with me, go on and talk. Okay, this one will be a 0. This one will be a 0. In fact, everything's going to be a 0 up until that last entry, A sub n, n. Okay, and that will be usually a non-zero entry. Okay, now I didn't bring this thing down far enough, so let me get it down like this. Everything below the main diagonal is a 0. The main diagonal usually is not 0, okay, but everything below it is. So this is called an upper triangular matrix, okay? Your lower triangular matrix, on the other hand, would start the same, A, 1, 1, but then you have your zeros here, 0, 0, dot, dot, dot. This pen is not doing well. Actually a 0, okay? Then A2, 1, A2, 2, and then 0, dot, 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 all the way out to 0 again. Then A sub 3, 1, A sub 3, 2, A sub 3, 3, dot, dot, dot. Those are all zeros, by the way, 0. And then we'll dot, dot, dot down here. The pen's dragging a lot. A sub n1, A sub n2, A sub n3, dot, 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 all the way down to A sub n. Dot, dot, dots here, dot, dot, dots everywhere. Okay? Everything above the main diagonal is a 0. Usually the main diagonal is not a 0 and doesn't have zeros in it, though it could, but usually it doesn't. But everything above it does. This is a lower triangular matrix. This is your upper triangular matrix. Okay? Now, if you had a matrix that was both upper and lower, then what that becomes, if it's upper, that means everything below the main diagonal is 0. But if it's also lower, that means everything above the main diagonal is 0. So that one would be this one. A1, 1, 0, 0, dot, 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 0, 0, A2, 2, 0, dot, 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 0, 0, 0, A3, 3, dot, 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 0, dot, 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 0, 0, 0 dot 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 a sub n n, and this is also 0 dot dot dot. Okay, so everything above the main diagonal is a 0. That makes it a lower triangular matrix. Everything below the main diagonal is a 0. That makes it an upper triangular matrix. But if it's both of those, what you have is called a diagonal matrix, because the only entries are on your diagonal. The only non-zero entries are on your diagonal. Okay, that's called a diagonal matrix. Okay, now if you are trying to find the determinant of any one of these three matrices, upper triangular, lower triangular, or diagonal matrix, guess what it is? It's just the product of the diagonal entries. Because guess what? If you did any of these others, they're all zeros. Any of these would be zeros, and certainly these and these would be zero. So the only product that's not a zero is your main diagonal. Here, here, or here. And that's why I said that most of the time your main diagonal does not have a zero in it, because if it does, the whole matrix, the determinant of the matrix is zero. Okay, so if that main diagonal for either upper triangular, lower triangular, or diagonal matrix, if all those entries in the main diagonal are non-zero, then you have a determinant that is also non-zero. Excuse me just a minute, I am losing it fast. I've had a really rough morning. By the way, my treatments on Thursday and Friday went incredibly well. I could sense from, especially Thursday, even though it was a 10% dosage, I could just feel heat all over in my body because the monoclonal antibody was really attacking those white blood cells, and I was hot. I mean, I could tell it was being very, very effective. Okay. Friday, when I had the 90% dose, I could tell a little bit of heat going on, but that 10% I think wiped out just about everything. The 90% was just cleaning up any that was left. Not all of it, but some of it. Now, the result of that, though, was because the 90% still had plenty of monoclonal antibodies attacking something, it probably attacked some of the red blood cells and platelets. So basically, I'm probably more anemic since the treatment than I was before, and I was very anemic before. However, every day I'm feeling a little better. But I have just been, it's just been really weird. I've not been sleeping well. Of course, I'm taking a diuretic too. That may have something to do with it. And I've just been feeling really weak, probably the anemia, incredibly weak. And then this morning, my stomach was just completely upset. But now that that's sort of cleared a little bit, I'm feeling so much better than I have since I started the treatment. So I think the treatment really messed up my system. Most of the time it doesn't, but it sure did this time. Hopefully that's better now. I feel better now than I did earlier this morning. I haven't been sleeping well, but quite often that has to do with, stomach upset too. And that's just the way it seems like I am. So I'm doing better. Sorry that we couldn't meet last Thursday. I didn't get home until right around 3 o'clock, so couldn't have met Thursday. Now, it seems like to me that y'all said you did want to meet on Friday to make up that class, but not this Friday. This Friday I've got to go to Georgia and take care of some business there, so we can't do it this Friday. But next Friday, I think that's what I understood y'all wanted to do. 8 o'clock, was that right? Okay, so 8 o'clock, not this coming Friday, okay, but next Friday, 8 o'clock, we'll do an hour and 15-minute class and catch up what we missed last Thursday. So I appreciate your wanting to catch that up. And things are getting much better. but I'm still very, very low in energy because of the anemia. So hold on just a minute. Let me. Boost energy with a little caffeine and sugar. Okay. Not the best thing to use, but it's all I got right now. Okay. Now, any questions on triangular matrices or diagonal matrices? Let's do an example with one. It's not really an example, but it's just doing one. Here's a matrix A. They love A, don't they? And here's what it is. 2, 3, -1. 0, -1, 2. 0, 0, 3. Okay? To find the determinant, guess what? Piece of cake. Why? Because this is an upper triangular matrix. Everything below the main diagonal is a 0. So you don't have to do expansion by cofactors. You don't have to expand the first two columns. All you have to do is multiply the elements in the main diagonal. That's all, folks. The determinant of A would then be -6. Done. 3 times 2 is 6, times a -1 is a -6. Okay, that's it. That's all there is to it. Okay, so that leads to theorem 3.2, and here's what it says. I almost feel like I ought to type this one out because it would be a little easier to read, but since I've got it on the screen, I'll go it. Okay, if A is a triangular matrix, okay, of order n, and by the way, triangular matrices have to be square. You can't have a rectangular triangular matrix. It has to be square matrix, okay, of order n. Then that implies its determinant is the product of the entries in the main diagonal. My writing stinks, but it writes so much better if I write cursive than I do printing. I don't know why. So in other words, if A is a triangular matrix, upper triangular, lower triangular, diagonal, it doesn't matter, any triangular matrix, then the determinant of A is simply the product of A11 times A22 times A33 dot 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 times A sub n n. Only those diagonal entries. Multiply them together, you got them. Okay. Any questions on that? All right, let's clear that out and let's do example 6. Now, here is a matrix A, their favorite of all time. It's a 2, 0, 0, 0. For -2, 0, 0. -5, 6, 1, 0, and 1, 5, 3, 3. Okay, there's a matrix A. What do you notice about it? it is a lower triangular matrix. Everything above the main diagonal is a 0. So what's the determinant of A? All you do is multiply those diagonal elements together. Let's say minus 4 times a 3 is minus 12. Done. That's it. Done. No expansion by cofactors, nothing. Multiply the main diagonal elements. Only works for triangular matrices. Diagonal matrices are triangular matrices, so only works for them. Either upper, lower, or diagonal. That does finish 3.1. Homework exercises here in 3.1. Any of the odds 1 through 11, they're all found at Calc Chat. They're also in the back of your book, by the way. Either 13 or 15, found at Calc Chat. 17's at Calc Chat. Any of the odds 19 to 31, all at Calc Chat. 33's at Calc Chat. 35 or 37 are at Calc Chat. 39 or 41 at Calc Chat. 43 is a true false. It has 3 parts to it, so that should be at Calc Chat. Either 45 or 47 should be at Calc Chat. Okay? 49 or 51 should be at Calc Chat. 53 should be at Calc Chat. Any of the odds 55 to 61 should be at Calc Chat. And any of the odds 63 to 67 should be at Calc Chat. And finally, 69 should be at Calc Chat. All right. That's it for 3.1. Any questions on 3.1? All right. We go to 12:45, right? I have to remind myself because all my classes end at different times, so I want to make sure I've got that right. So let's move on to 3.2. Determinants and elementary operations. Okay? Here are the 3 objectives here. We'll use elementary row operations to evaluate a determinant. We'll use elementary column operations, which we've never done before, to evaluate a determinant, and we'll recognize conditions that yield 0 determinants and what that means for us. Okay, so I think I'm going to clear this screen and we'll pick up and do here. Okay, now they start with a question. Okay, and here's what their question is. Which of these determinants is easier to evaluate? So here's determinant of A. 1 minus 2, 3, 1, 4, negative 6, 3, 2, negative 2, 4, negative 9, negative 3, and 3, negative 6, 9, 2. Frankly, doesn't look very inviting. Okay, or determinant of B, which would be 1, negative 2, 3, 1, 0, 2, negative 9, negative 2, 0, 0, negative 3, negative 1, this is so aggravating. Okay, and 0, 0, 0, negative 1. Which of those you think would be easier to evaluate the determinant? A or B? Anybody? Well, look at B. It's an upper triangular matrix. To figure out its determinant, just multiply the main diagonal entries. That's all, folks. That would be 3 times 2 is 6. That's it. Now, what may be hard for you to believe, it has the same determinant as A, okay? But it sure doesn't look that way. If you were trying to do A, absolutely no zeros anywhere in A, so you would have to do expansion by cofactors at least once, okay? And then you'd have a 3 by 3 and you can go from there. But it's still a lot of work. Now, is that someone trying to reach me, or is that just noise? Okay. Now, they actually are going to do A, so let's do it. And it really doesn't matter which one you do, they happen to do the first row. So let's do it, okay? Let's do A. We've already figured out what B is. That is 6. The determinant of B is 6. You can do that in your head. 2 times 3 is 6. Okay, so let's do the determinant of A. Well, let's start with, I think they're going to do the first row. Going to go that way. So let's do first row, first column. The sign of this position is a 1, so that's just going to be a 1 times the 3 by 3 that's left, the determinant of that. Well, that's not going to be that hard to do because it's a minus 6, 3, 2, 4, negative 9, negative 3. Now, I'm not doing cofactor, I'm doing it the easy way. Negative 6, 9, 2, and then expand the first two columns. Minus 6, 3, 4, negative 9, 6, negative 6, 9. It's still going to be a pain, okay? I promise you that, okay? So let's do it. Down diagonal here, we know the 1 that's just going to be a 1. So this is just going to be that. That's a 54 times 2 is 108, I think it is. Everybody agree? 54 times 2 is 108. Next down diagonal is going to be 9 times 6 is 72 plus 72. Believe that's right. 9 times 6. Yeah. Is that right? No, it isn't. 54. That's 54. I don't know where my brain is today. That's a 54. Okay. 9 times 6 is 54. Positive, by the way. And then the next main diagonal is going to be a 36 times 2 is a 72. Okay? That's your down diagonals. So I'm going to erase those just because they're kind of in the way here. Okay? And then let's do the up diagonals. Of course, they'll be the negative of that. And that's going to be, would have been a 54 times 2, which is a 108, but it's negative, so that's going to wipe that one out. Okay? Then the next one would have been a, that's an 18 times 9. So 18 times 9, and that's going to be 72, 162. And that's going to be a minus 162 because it's an up diagonal. Okay? And then the last one is going to be a minus 24. It would have been a 24, but it's upside, so minus 24. Okay? So let's see what we've got. Let's add these two together. You get a 126 minus, this isn't working out right. I think I did something wrong. Okay. minus a 1 Oh, I'm sorry. I only did one thing of them. Sorry about that. Duh. I only did this one. And I still got to do the others too. And you can see what a pain in the neck that would be. I only did this one. Okay. We've still got to do this one and that one and that one. Okay. That goes on forever. Okay. What a royal pain. Okay. The answer is going to be positive 6. So I didn't work this out. I'll let you look at it in the book and you'll see that's what it becomes. Okay. Now, this was so much easier, wasn't it? Way easier. Now, what we're going to do in just a little bit, but let's go on evaluate it first, and then we'll get down to the brass tacks. Let's do example 1. Okay. So I'm going to clear this. Excuse me. Let's do this determinant. Now these are going to be easier. They're 2 by 2s. Okay. Let's do the determinant of matrix A. Determinant of matrix A is a 2 by 2. It's a 2, -3, 1, 4. Well, we know what that is. 8 minus a minus 3, that would be 11, right? Now, matrix B here, how we're going to get matrix B is determinant of B. That's going to be 1, 4, 2, -3. What have we done there? We exchanged the 2 rows. That's all we did. Okay? But let's do what its determinant is, and that is -3 minus 8. That's minus 11. Exchange 2 rows, you negate the determinant. That's it. You negate the determinant. Okay? That's the A part here. Let's look at the B part. Here's matrix A. 1, -3. Wouldn't use the same one, would they? 1, -3. 2, -4. Okay, let's do that determinant. That would be a -4 plus 6. That would be a 2. Okay. Now, here's matrix B. Now I'm going to tell you what I'm going to do to get B. You have a 1 here, so I'm going to multiply -2 times row 1 plus row 2. Okay? That's sort of hard to read. Okay. Excuse me. I've got to get something else to drink. Sorry. Here's James. Good deal. Let me get James in here. Perfect attendance today, team. Way to go. All right. So far, 2 weeks in a row, 2 Tuesdays in a row, perfect attendance both times. Way to go. Okay, James, we're in Chapter 3, Determinants, Section 3.2, Determinants and Elementary Operations. We're doing Example 1, the bottom of page 118, and we're doing some of these row operations. Now, what we're doing here, what we did in the A part up here, was just exchange 2 rows. I can't get my pen to show up right here. We exchanged the top and the bottom row, and we found that the determinants negated each other. This one, we're going to do add a multiple of 1 row to the other row. just like we always did in row reduction. So negative 2 times row 1, add it to row 2, what do you get? Well, row 1 we're using, so that's 1, negative 3, not going to change anything there, okay? But here we're going to do negative 2 times 1 is negative 2 plus 2 is 0, and negative 2 times negative 3 is 6, minus 4 is 2, okay? What's the determinant of that reduced matrix? That would be 2. And that was exactly what the determinant was here, okay? Now this doesn't prove it, but it indicates there seems to be a pattern, okay? Now we're going to do one more. Here is determinant of A, and that's going to be the determinant of 2, negative 8, negative 2, 9. Okay, let's do that determinant. Again, 2 by 2s are easy. 18 minus, because it's up diagonal, 16, that would be 2. Okay, now what we're going to do to B here is another elementary row operation. We're going to divide row 1 divided by 2 is going to be the new row 1. Okay, so what does that become? 1 minus 4, negative 2, 9. Let's do that determinant. What do we get? 9 minus 8 is 1. Well, you divided a row by 2, you divide your determinant by 2. Exchange 2 rows, you negate the determinant. Divide by a constant, or multiply by a constant, you multiply or divide the determinant by that same constant. But if you're adding a multiple of one row to another row, it doesn't change the determinant at all. Okay, which is very encouraging, because let's go to top of the next page. Okay, all right, to clear my drawings. Here's what theorem 3.3 says. Let's let A and B be square matrices. Okay, now what they don't say, they're the same size square matrix. Okay, they should say of order n or whatever. Okay, now there's one other thing I want to say. I forgot to say it, but I'll come back and say it in a minute. Okay, here are the 3 elements from this. When B is obtained, I was going to say this may be better to type. I don't know, I'll just do it this way. When B, this is just really awkward writing, is obtained, and for some reason it's so much easier to, it prints better, it writes better if I do it cursive than if I do it printing. I don't know why. If B is obtained from A by interchanging two rows of A then the determinant of B is equal to minus the determinant of A. By exchanging 2 rows, you're going to negate your determinant. Okay? That's what the first thing showed before. Number 2. when B is obtained from A by, this is so aggravating, adding a multiple of a row of A to another row of A, yuck, this is hard to write. My phone's ringing downstairs. Okay, when you do that, the determinant of B is exactly the same as the determinant of A. That's the good news. Oops, only need one bar there. And the third one, okay, when B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of B is equal to C times the determinant of A. Now, the little remark just to the left of this theorem is what I meant to do and I forgot to. Is this the same one? No, it's not the same one. But this is a fairly simple example. If you have the determinant of 2, 4, 1, 3, okay, and what you do is factor out a 2 from that first row. It doesn't matter, it doesn't have to come from everything, just for the first row, times, that would be a 1, 2, 1, 3. That would give you the same results. Let's see what we get here. 6 minus 4 is 2, and this would be 2 times 3 minus 2 is 1, and that would be 2 also. So you can just factor out. It's not factoring out from every term, it's factoring out from one row or one column, either one. Okay, one row or one column. All right. Now, those are our three rules. This one changes the sign, this one changes by a factor, this one stays the same. That staying the same, I like it. Okay, so let's do example 2. Can I erase this now? Okay. Find the determinant of this. Here's matrix A, their favorite of all time. 0, negative 7, 14. Okay, 1, 2, negative 2. 0, 3, negative 8. Okay, and we're wanting to find the determinant. Now, I'm going to do this a couple of different ways if I have time. We don't have much time. We only have about 7 minutes. So let's first do what I consider the easy way. Let's just expand that and do it. So what I'm going to do is take this off and expand it and do it. Okay, expand the first two rows. 0, -7, 1, 2, and 0, 3. Okay, and we're going to do our expansion here. That's a 0, this is a 0, and this is a, wow, 52? I believe that's right. No, 42. So that's going to be 42. Okay, now I'm going to erase that. Okay, erase this one, and that one. Okay, now I'm going to do my up diagonals. That one's going to be a 0. Ooh, this one's going to be that's going to be again a 42 times a -2 would be 84, but it's a plus 84, so that's going to be a 84. This is getting messier than I thought. I botched something up there, didn't I? That up diagonal, that up diagonal. No, yeah, I did botch it up. This one was okay, I think. This one went this way. That's a 0. Okay, sorry about that. My lines are not very straight. Okay, this is a 0. Okay, and then this will be a minus 56. And that should add to be a negative 14. Okay, now that's what I got. Yeah, negative 14. Now, that was one way. That's sort of our shortcut way. But let's see what we can do this way. Notice that this had a factor of 7 in that first row. I can't get my, there it is. Okay, so let's do this. That determinant of A would be, just like they did in that margin note up there, let's factor out a 7. Okay, times the determinant of 0, -1, 2. 1, 2, I can't read my writing there. Is that a -2? Yeah, -2. And then, I can't read my writing again, 0, 3, -8. 0, 3, -8. Now I want to do that again, okay? Because this has a factor of 2 in it everywhere. So if you factored that 2 out as well, I think, I'm going to try this anyway, 2 times 7 is 14, and that would then be the determinant of 0, -1, 1, 1, 2, -1, and 0, 3, -4. Okay, now this is getting a little sketchy because, okay, now that one I think I would then want to do, and I'm not saying this is any easier, okay, but let's do that expansion and do a 0, -1, a 1, 2, and a 0, 3. And let's do that expansion. So this will be a 14 times down diagonal 0, down diagonal 0, down diagonal 3. Okay, I'm going to try to erase some of those. And do my up diagonals. That would be a 0, that would be a 0, and this would be a -4. I didn't write down, oh, I wrote down my 3, but it disappeared. 3, and this would be a -4, right? And what do we get? -14. So you see, sure enough, factoring out makes it a little easier. The numbers are much smaller, and we still got -14. That is your answer. Now, how do we do on time? 1 minute left. Okay, so that gave us -14. Now, I actually did it twice. Okay, I factored out the 7 from the first row and the 2 from the third column. Perfectly legal. Just keep up with what you're doing there and then proceed. There is a blurb on page 119 on Augustin Louis Cauchy, I guess is how you pronounce it. And it gives quite a bit there on him. This cannot be your source for your paper, but it can be the source for the idea for the paper. Now, it shows him being a very young looking mathematician, but when you look at his age, he lived to be a ripe old age of 68. So this was a picture made when he was quite young, drawing or whatever. All right, so there's a potential paper topic. Hint, hint, if you haven't done your research paper, try to get that done. And we are now run out of time. Sorry about that. Let me change my mark here on the page, and we will begin next time on page 120. I'll just begin at the very top of the page, and we'll go from there. Any questions on anything we've done so far? Homework exercises in 3.2. I think you can do any of the odds 1 through 19. Okay? I think you can do either 21 or 23. And I think you can do any of the odds 25 to 31, well, 25 to 35. And we'll stop there and pick up the rest of those next time. Okay? Good deal. Any last thoughts, parting shots, questions? Okay. I'm going to stop the sharing. Sick and tired of sharing here. If there are no questions, I'll go on and end the meeting for everybody. Okay, I can't remember if I said this early because we only have one person here. Remember, next Tuesday is what? Voting day. Please, folks, I hope you're registered to vote. If you are, I hope you've already voted. We have. We went quite early, I think in September sometime when we were first able to. Not first, but very soon after they opened it up, and we've already voted. Please vote, folks. Please do. Okay? And what's more than that, next Tuesday, not Thursday, we'll have a fair class on Thursday, I think. Next Tuesday, who knows how the internet's going to be. It could be everybody in the world is out there trying to track what's going on. So it may be a little sketchy then. We're going to still try to have class. Hopefully it won't be a problem now. I have a feeling my afternoon class, that might get a lot worse. But the morning class shouldn't be too bad. So anyway, I hope you vote, or if you haven't voted already, and we'll see you on Thursday. Okay? All right. Let me end the meeting for us all unless there's any questions. Okay. Take care. I'll see all of you tomorrow. Okay? Take care. Bye-bye.